Hello, everyone. This is Vishaka, founder of Gurukul Academy. We welcome you to the fifth episode of the Scientific Saturday Lecture. Our guest for today is internationally renowned physicist Professor Keith Riles. Welcome, Professor. He carries out research into the fundamental forces of nature, working in both gravitational waves and elementary particle physics. He is also a member of the Ligo scientific collaboration, which in September 2015 discovered gravitational waves from the merger of the two massive black holes. Professor Riles has also spent part of his research time in recent years studying the physics potential and the detector requirements of a future linear electron positron collider with a center of mass energy of 350 giga electron volt and higher.
Hi, I'm Rishabh, founder and admin of the Secrets of the Universe channel. So, before we invite Professor Keith Riles for his lecture, I would like to remind everyone that we'll be taking questions after the presentation. So, you all can post your questions and queries in the comment section, and we'll be taking it once the lecture is over. We welcome you, sir. We are very fortunate and privileged to have you with us today. Without further ado, we request Professor Riles to begin this session.
For inviting me. I appreciate this opportunity to get.
Just a second, we're facing.
Just a minute, sir.
Yes, sir. Thank you so much for joining us today, sir. I
Thank
think
you.
all's well, and we can go ahead with the
I
lecture.
can go ahead and begin. Okay. All right. Well, thank you again for inviting me. It's a nice opportunity to speak with all of you. I've entitled this presentation From Atometers to Gigaparsecs, Gravitational Waves Define a New Astronomy, because I want to try to explain to you how it is that measuring distances at the level of atometers here on the surface of the Earth allows us to probe the deepest parts of the universe at gigaparsec levels, gigaparsec distances, where a parsec is about 3 light years roughly. All of these images you see on this page correspond to various gravitational wave detections, which I'll talk about later on. Let me begin by contrasting the classical Isaac Newton perspective on gravity with what we think is now the correct Einsteinian view. So in Newton's perspective, forces that are gravitational are relatively simple. If you have two masses like the sun and the earth, and you treat them as being ideal spheres, then the force between those two objects is equal to Newton's gravitational constant, big G, times the product of the two masses of the sun and the earth, divided by the square of the distance between them. And that particular formula has been extremely successful over centuries in predicting the motions of objects in our solar system. And in more generally, that beyond our solar system into the galaxy, and in describing the behavior of galaxies in the universe. Nonetheless, there is something wrong with this formula, and Newton himself understood that. To see how this doesn't really make sense, imagine that the sun, shown here, this yellow ball, were to suddenly explode into two pieces that go in different directions. According to this formula, that would be instantaneously felt here on the Earth. The force would naturally change. It would be the force between the Earth and two other objects, and that would happen instantaneously. And that really doesn't make any sense. And Newton realized that. In fact, he called it a great absurdity. But he didn't know how to solve the problem. He knew it didn't make any sense for this instantaneous action at a distance to be part of nature. It didn't mesh with anything else we know about nature. But he didn't know how to deal with it. And like any good physicist, and he was one of the great physicists of all time, he basically swept that problem under the rug and said, okay, I don't know how to deal with this, but I do know how to do calculations. And he just proceeded. Now, there were a number of physicists and mathematicians following Newton, over the centuries who tried to solve this problem, but they all came at it from the same kind of a classical perspective. The solution to this came from Einstein, who took a completely different approach. And instead of thinking in terms of forces between objects, Einstein thought in terms of the warping of space by mass. And so in this picture, we have again the sun and the earth depicted as these two balls, and the sun is warping the space around it. There is this two-dimensional grid that, or a mesh, that is a two-dimensional analog of what is happening in three-dimensional space. The sun is warping the space around it, and the Earth, which is in the vicinity of the sun, is compelled to obey that warp. And so it travels in a rough circle around the sun because of the warping of the space around the sun. And likewise, you can see that the Earth itself also creates a dimple in this two-dimensional analog to what's happening in three-dimensional space. So conceptually, that's what we think is happening. Mathematically, it's represented by this equation at the top, known as Einstein's field equations. It's deceptively compact. If you try to unpack that to see what it actually means, it rapidly expands into something that's quite cumbersome to work with. But setting aside the mathematics, you can think of it as a conceptual sentence that was written by John Wheeler, the fellow who coined the phrase black hole. And the way he put it was that matter tells space-time how to curve, and then curved space tells matter how to move. They feed back on each other, space and matter. Now, what I've shown you here is a relatively static picture. The Earth is traveling around the sun at a relatively low velocity. It may seem high compared to the speed of a car on a highway, but it's still only about 1 part in 10,000 of the speed of light. So it's not a relativistic motion. But there are other processes in the universe that are truly relativistic. And one would be the in spiral, I call it the death spiral, of two neutron stars or black holes. In the final moments, as these two stars come together, get closer and closer because they are emitting gravitational radiation, which causes them to lose energy, they spiral into each other eventually. In the last few moments before they collide with each other, these objects are traveling at large fractions of the speed of light. I'll show you an example of that a bit later. And so instead of having just a static warping of space, it's more appropriate to think of it as a swirling of space by this extremely dynamic and somewhat violent process. And so those swirls become gravitational waves, and by the time they reach us, they are tiny, tiny ripples, and it's very difficult to detect them. But they are representing an enormous amount of energy that was released in this process. I'll come back to that point a bit later. This little animation represents what happens when a gravitational wave impinges upon some object. So what we can picture here is a ring of test masses just floating out in outer space, shown by the red dots, arranged in this ring. And imagine a gravitational wave is hitting this ring of masses normal to the plane, perpendicular to the plane. Then it will stretch space in one direction while compressing it in the other, and then alternate back and forth. This is what's known as a quadrupolar distortion, and ultimately it comes from the quadrupolar distortion to the source itself, the thing that is creating gravitational radiation. So how would you detect something like that? Let me show you this animation, and I'll stop and start it a few times as we go along. Over here is a representation of a laser at the bottom left, and the light coming out of the laser hits this beam splitter that's oriented at 45 degrees. And so when the light hits that beam splitter, it gets split. Half goes to the left, half goes toward the right. And this light that's going along, that we're watching right now, is on what's known as the X arm, and the light over here is going into the Y arm. That light comes back and it recombines. The light has bounced off a mirror on each end of each arm, and the light has come back to the beam splitter, recombined. Some of the light goes back to the laser, but some of the light goes this way. In each case, you get nominally a 50% split. But if you've ever studied interference phenomena, you know that it's a little more complicated than just the 50% split each way. What is happening here is that we are getting crest from one wave coming back from the X arm, shown in yellow, that is coinciding with the trough of the waves coming back from the Y arm. That means that the two waves cancel each other. The electric fields that are embedded in these laser beams are exactly canceling each other. And we get what's known as destructive interference of the light that goes off in this direction toward our detector. So let me continue running the animation. That light hits the photodetector and is detected. Now, normally what we would do is just run the detector in this mode. But if you let a gravitational wave come along that has this quadrupolar distortion so that one arm stretches at the same time the other arm is compressing, then you disturb that very delicate balance imposed by the position of the beam splitter. And so you get this flickering of light. You alternate between constructive and destructive interference. And so if you place a detector over here, then that detector will measure a flickering light intensity, which is a direct measure of the passage of the gravitational wave. So that's the essence of the interferometers that go into LIGO and Virgo and something called COGRA and GEO, and eventually what will become LIGO India. These are micro interferometers on a vast scale that are trying to detect flickers of light from the passage of a gravitational wave that is stretching and compressing the arms of the interferometer alternatingly. Here are pictures, over aerial pictures of the observatory in Hanford, Washington, LIGO Hanford, and here's one in Livingston, Louisiana, so LIGO Livingston. These two interferometers are separated by about 3,000 kilometers, which is about 10 milliseconds of light time, and should, according to Einstein, also correspond to 10 milliseconds of gravitational wave propagation time, because gravitational waves and light should propagate at the common speed limit of the universe, which we normally call the speed of light. Now, the reason these two observatories are so far apart is that we want to validate that they've seen something real that is truly astrophysical and not terrestrial by the fact that we would see signals in a very short space of time, roughly within 10 milliseconds, that look just like each other. And that eliminates almost all of the terrestrial types of disturbances you might worry about, because there are many different ways to produce disturbances in a Michelson interferometer. The ground is moving all of the time, everywhere on the Earth. And sometimes the ground moves enough to actually disturb your interferometer. And so you want to make sure you get rid of those kind of random effects. And one way to do that is to have the observatories so far apart. In addition, the fact that they're so far apart gives us some directionality in terms of where a source might exist in the sky that gives us a common signal, the two interferometers. By looking at the time difference between when the signals arrive at the two observatories, we can infer that the source was somewhere on a ring in the sky that is consistent with that time offset. So one extreme would be seeing a signal at Hanford and then 10 milliseconds later seeing it at Livingston. That would mean that the signal was directly opposite Hanford from Livingston along a line. But more generally, you're going to get something ranging between minus 10 and plus 10 milliseconds. That'll tell you that somewhere on the sky there was a source. Now we can do a little bit better than that, in fact, because the interferometers have a directionality to them. They're more sensitive to certain points in the sky than other points. And so that tends to favor certain parts of the ring over others. And I'll show you some examples of that shortly. But the triangulation is based primarily on the timing, and that is then refined by our understanding of the directionality of the interferometers. We work very closely with the Virgo collaboration, which has its own similar kind of interferometer in Italy near Pisa. It's not quite as long as LIGO, and it's not quite as sensitive as LIGO, but it's comparable. And so it helps our triangulation enormously. Even if they see a weak signal, which is sometimes the case, it still helps our triangulation by about an order of magnitude, because we get another point on the Earth at which we're measuring the arrival time of a signal. And even if we don't measure the signal itself all that accurately, if we can measure the arrival time, that gives us an enormous amount of information about where that source was on the sky. And again, I'll show you an example. There's actually a growing global interferometer network. I've talked about the two LIGO interferometers in the United States. There's also Virgo in Italy. There's something called GEO in Germany, which is much less sensitive than LIGO and Virgo, but which is nonetheless useful because when LIGO and Virgo are being improved upon, being upgraded for, say, the next observing run, we have at least one detector on the Earth that is running all the time, just in case something happens that's very gravitationally loud here in our own galaxy, like a supernova. So they often run in what's called astrowatch mode, just in case something happens. We don't want to completely miss it. And then there's also a new detector in Japan called Kagra, which eventually we hope will be as sensitive as LIGO and Virgo, but right now it is still in a commissioning stage. And then in the future, as you probably all know, we will have LIGO India, which will be essentially another version of LIGO, but on a different part of the Earth's surface. And again, that is going to dramatically improve our triangulation, our ability to say where a source came from. So that's a very exciting part of our future, and we're looking forward to that. This shows you a group of LIGO logos from all the different institutions in the LIGO scientific collaboration. It has grown enormously over the years. When I joined more than 20 years ago, when we founded the collaboration, there were probably 1/5 the number of institutions and 1/5 the number of people that you see here. But it takes an enormous number of people to do science on this scale. So our first detection, as was mentioned in the introduction, was in September of 2015. We call that event GW 150914 because it was 2015, September 14th. It was right at the start of our observing run, the very first one with what's known as advanced LIGO. And what you see here in red is almost the raw data seen in the LIGO Hanford instrument. There's been a little bit of filtering done to make it more presentable, but not much. And then over on the right in blue is a signal seen in Livingston, Louisiana. Now, the red curve has been moved over to the right-hand column. It has been flipped upside down because the two observatories happen to be rotated 90 degrees with respect to each other. So you have to, that gives you a sign flip because of the quadrupolar nature of the distortion. And the red curve has been shifted over by about 7 milliseconds. And notice that 7 milliseconds is less than 10 milliseconds. So it was within the window that would correspond to a physical signal. And you can see that these two squiggles agree with each other remarkably well, indicating this was a truly astrophysical source. And it was our very first gravitational wave detection. This next column shows you basically reconstructions. It shows you, in some sense, fitted analytic curves or functions to what was measured in the data. And overlaying with that is what you get from an exact calculation in Einstein's general relativity using numerical techniques known as numerical relativity. And we see beautiful agreement between Einstein's predictions for what a detection like this should look like and what we actually observe in the data. This last row shows you what are known as spectrograms. Again, the horizontal axis is time scale, and it's only about 0.2 of a second long. And the vertical scale is the frequency on a logarithmic scale. And the color shows you the intensity of the signal. And so what we see here in both the Hanford data on the left and the Livingston data on the right is an increase in the intensity and an increase in the frequency in the very last moments when these two objects, which are very massive black holes, come together. I'll show you a little cartoon in a moment that gives you a little more insight into why it has this particular shape. But basically, we're seeing a chirpy behavior where both the amplitude and the frequency of the signal are ramping up dramatically in the very final moments. We call this the golden event, and then later we called it the first golden event because we've had some other nice looking events since then. Here are the source parameters that have been inferred from this detection of two massive black holes. We have a 36 solar mass black hole, so a black hole with a mass of 36 suns. that interacted with a slightly lighter black hole with 29 solar masses. And when they came together, they merged to form a single final black hole whose mass was 62 solar masses. Now, if you look at those numbers, you might be bothered by them because 36 and 29 does not add up to 62. There's something missing there. And what's missing is the fact that in this process, as the two black holes came together, they emitted an enormous amount of gravitational wave energy, which took away from their mass. Remember, according to Einstein, energy and mass are equivalent. Well, if you radiate that energy away, you're radiating away mass. And so about 3 solar masses of energy was radiated away in gravitational waves. And the quote luminosity, kind of an invisible form of luminosity, but nonetheless, that energy per unit time that came out was brighter than the entire rest of the universe for that brief period of time of a tiny fraction of a second. So there's an enormous amount of energy that is emitted in these mergers of compact objects like black holes and neutron stars. And in fact, we need to have those kinds of energies in order to produce gravitational waves that we can detect here on the Earth. Let me play for you a little animation that has both spectrograms and audio to go along with it. You may have seen this before, but it's going to play for you twice in a row the spectrogram seen in Hanford and Livingston simultaneously, along with the audio that goes with that. Remember that these frequencies are in the audio range. You can literally take a gravitational wave data channel, plug it into a speaker or into a pair of headphones, and just listen to the data. And sometimes the operators in the control rooms at the observatories do exactly that. Not so much to catch a detection, but just to monitor the quality of the detector noise. So I'm going to play that for you. It's going to play the signal twice, and then it's going to play the signal again twice with the frequency deliberately upshifted by several hundred hertz to make it a little bit more audible, so it's easier to pick up on the signal. And then it's going to do the whole thing over altogether. I think there will be 8 of these altogether. Oops, didn't mean to do it. Here we go. Okay, so there's actual frequency and then upshifted frequency. Okay, now as I said, you would not count on detecting a signal like that just by listening in headphones. You have to use sophisticated signal processing techniques in order to detect these things in a systematic way that you believe. Here's another animation you may have seen before, but basically what has been done here is to carry out a numerical relativity simulation. So this is about as exact as it gets for modeling what was happening in this particular event, the first detection. What you imagine is that you have the two black holes that are in space between you and the Milky Way. And so we're looking at an arbitrary field of stars in the Milky Way and seeing how the light from those stars comes to us as they go around and pass by these black holes. That warping of space I talked about earlier is also analogous to the warping of the deflection of light when it passes through a lens or passes from one medium to another with a different index of refraction. So what we're seeing here is a field of stars as perceived through something like a double lens of two black holes. And in fact, if you look closely, you'll find that there are cases where the same star appears in more than one place on this image, because there's more than one way for the light to come around in the vicinity of those black holes. Now let's let those black holes merge in slow motion and see how that distortion is changing. So as the two black holes come together, we see that the light from the stars is indeed being changed in the way it's deflected around these black holes. Eventually, the two black holes will come together and they will merge to form a single black hole. That's about to happen right now. And then that final black hole, in some sense, kind of shakes off its excess energy and angular momentum, just leaving behind a relatively static black hole. And it has this characteristic dark ring around it known as an Einstein ring. If there happened to be a star directly behind it, it would be a bright ring. But in this case, we see a dark ring. So that's a numerical relativity simulation of what happened, where we allow the light of stars behind the black hole in the simulation to show us what's happening to the warping of space around those holes. So if we look at this event a little bit more, it helps to look conceptually at the different phases of this merger process. We have this end spiral phase where we have two distinct black holes that are clearly separated, and you can see that in the simulation. Then there's a merger phase where they come together, and then there's this final stage called the ring down where they shake off that excess energy and angular momentum. And what we can do is compare what we see in this in spiral stage to what we see in the merger and the ring down stage. Stephen Hawking is famous for a number of things, but one thing he is famous for is saying that black holes have no hair. And what he meant by that was that black holes are characterized entirely by their mass, their angular momentum, and their electric charge, if they have any appreciable electric charge, which we don't think they normally do. And so that means that when you bring two black holes together to form a third black hole, the process ought to be relatively well defined based on the initial conditions of the initial black holes. And so if you were to see something that deviated from Einstein's relativity, indicating something that is sometimes called hair, meaning that there's something left over after the merger of the two black holes, that would indicate that there was something wrong with Einstein's theory. So the fact that we see such beautiful agreement here between the reconstructed waveforms fitted to the data and what is predicted by numerical relativity seems to indicate that, in fact, black holes do not have at least long, scraggly hair. Maybe they have crew cuts. Maybe if we probe deeper in our data, we will eventually see something that deviates from Einstein's prediction. But right now, just based on this first single detection, and has been the case in all the detections we've made since then, we've seen no evidence of something different about black holes after they come together to form a third black hole. While I'm showing you this graph, let me point out this one at the bottom here. The dark curve shows you the black hole separation in units on the right-hand y-axis of the Schwarzschild radius, or the horizon radius of the final black hole. And so the two black holes come closer and closer together, and, and then they merge. The green curve shows you the relative velocity, which in some sense is the vector difference between the velocity, but basically the addition of their magnitudes, of their speeds, in units of the speed of light. And you can see that in the final moments just before merger, these two objects are traveling at a total speed of almost 60% of the speed of light. So it's an extremely dynamic and, of course, violent process when two black holes come together. In our first observing run, what was called the 01 observing run in fall of 2015, we had two very clean detections. We had the one I've been talking about, GW 150914, and we had another one the day after Christmas, 151226, which was not as strong, but nonetheless qualified as a 5 sigma detection, something that was truly statistically extremely significant. And so that was a nice pair of discoveries. Later, we realized that another event that we thought was marginal at the time actually was pretty solid. So we think we actually had 3 good detections from that run. We then had another observing run called 02, which began in November of 2016 and ran through August of 2017. I'm showing you some examples of different spectrograms and waveforms seen in these different events. So there was one in January 4th of 2017, another one here, June 8th of 2017. And we learned something from these events. But this one down here is special. The reason this one is special is that this was taken not long after Virgo joined our observing run. They were not quite ready for data taking in the first observing run, 01, and they were trying to improve their sensitivity during most of 02, and they got it up to an interesting level just before the end of that run. So they ran with us for 1 month at the end of 02, and it was a glorious month, as you'll see. So the first thing to note is that we now have a third spectrogram and a third waveform to go with it. So that means that Virgo was working. It saw a signal. It was not a very strong signal compared to what was seen in the Hanford data and the Livingston data, but nonetheless, that was statistically significant. And that told us that Virgo was now detecting gravitational waves. And for this particular event, it helped with the triangulation of the event. So this blue banana thing here is basically the favored region from the LIGO, Hanford, and Livingston interferometers alone. Remember I said earlier that we use triangulation to determine a ring on the sky. Well, this is basically part of that ring, but it's the part of the ring that is favored by the directionality of the two interferometers together. What Virgo did by giving us that extra triangulation point on the Earth's surface was to reduce the region of possible source location down eventually to this green blob based on a refined analysis. So advanced Virgo has added dramatically to our ability to triangulate sources. And that's very useful for electromagnetic or photon astronomers who use optical telescopes or radio telescopes or X-ray telescopes to look for the corresponding events in the electromagnetic realm instead of the gravitational wave realm. Now, you might naturally ask, well, why would we expect to see anything from two black holes merging to form a third black hole? What is there to see electromagnetically or in any wavelength? And the answer is we're not sure. There may not be anything, although there is some evidence that at least on one occasion there was some kind of electromagnetic flash. But what is of more interest to us is not so much this case of two black holes coming together to form a third black hole, but the case where one of the initial stars is a neutron star. So something that's not quite as compact as a black hole is still basically matter, nuclear matter. In that case, when the star comes together with the other star, and ideally the best case would be two neutron stars coming together, you're going to have some extra material left over that does not get swallowed up in the black hole. And that can easily lead to electromagnetic light that can be seen in different wavelengths. And I'll illustrate that in just a moment. This is our second golden event. This was seen also in August of 2017. This shows you the Hanford spectrogram. This is the Livingston spectrogram, and this is the Virgo spectrogram on the bottom. Notice that the time scale here is not a fraction of a second or even a second and 2 seconds. It's 30 seconds. This is a much longer lived event. That is to say, we could see the signal in our detectors for a much longer period of time. And the reason for that is that these were very light objects. These were basically two neutron stars instead of two very massive black holes. Now, the signal is extremely clear in the Livingston data, and you can see it pretty well in the Hanford data. You do not see it in the Virgo data at all. And I'll come back to that in a moment. This event also has other names, GRB 170817A, because it was seen as a gamma ray burst too, and also has some other oddball names that have to do with the optical detections of something associated with this event. Let me play for you what this event sounded like. Depending on the quality of the speaker that you're listening through, you may or may not be able to hear some of the low frequency sounds, but this gives you a sense of what this event sounds like in the raw data. Now, at some point, as you follow along with the spectrogram, you can see the trace of the signal again, and you'll get a sense of where the signal's frequency should be. Right now, it's still pretty low, around 50 hertz or so. Very hard to hear. But if you want to challenge yourself, close your eyes and try to listen for when the merger happens. Okay, I don't know if you're able to hear that, but I've heard this enough times. I can easily pick out that sound of the chirp in the background of the noise. Let me play for you the same signal without the noise, just extracting the pure signal out. And you won't be able to hear it unless you have really good low frequency speakers for a while, but eventually it will become audible as we start creeping up in frequency here. And the signal has been amplified. There we go. Okay, so it's much easier to hear when you don't have the noise in the background. So that chirpy sound where the intensity and the frequency increase sharply at the end is something we had been hoping to hear for a long, long time. Let me play for you another snippet of that same spectrogram on the bottom here. But on the top, I'm going to show you the basically the raw data from a gamma ray satellite that was collecting data at the same time and with whom we were collaborating, coordinating. And you can get some idea of why we were so excited by this event. So there's our gravitational wave spectrogram at the bottom, raw counts in the gamma ray detector at the top. And then a signal is seen in the gamma ray satellite about 1.7 seconds after the merger. Now the audio ding was put in by hand, but basically something happened. The satellite saw something quite interesting shortly after we detected the gravitational waves. And so that was basically saying that the process that led to the collision of the two neutron stars had produced what's known as a gamma ray jet. And those gamma rays came to the Earth, and the gamma rays took a little bit longer to form than the original gravitational wave signal, because the gamma rays have to come out through a complicated process in the vicinity of the stars. I'll show you an animation of that in just a moment. But basically, depending on the modeling you have for how long it takes the gamma rays to be produced, you can set limits on the difference between the speed of light and the speed of gravitational waves. These are two signals that came from very, very far away, roughly 130 million light years away, and yet they arrived together at the Earth within a couple of seconds of each other. And it could be that that the 1.7 second difference was exactly what you'd expect from the generation of the gamma rays to begin with, but maybe the difference is in part due to a difference between the two speeds of gravity and light. So you can do a relatively simple calculation, and what you find is that the relative difference between the gravitational wave speed and the speed of light, c, is at the level of better than 10 to the minus 14. So our initial assumption that the speed of gravity would be the same as the speed of light was confirmed with remarkable precision by this single event. Let me play for you an animation from NASA. So it has pretty high production values, although it's a little bit hokey. This is showing you what's happening as these two neutron stars come together. And I'll freeze it right after they hit each other. Okay, so here we have these jets of matter flying apart along a direction that's roughly normal, roughly perpendicular to the orbital plane of the two neutron stars. And that jet is going to produce gamma rays that are eventually seen by the satellite. You can imagine the Earth is somewhere out here in the line of sight of that jet. But let me continue the animation because other stuff is happening. It's also quite interesting. So you see a lot of matter around here in the vicinity of the aftermath of the merger. The two neutron stars are presumably swallowed up into a black hole, and not all of that matter gets swallowed up. Some of it is left around the equatorial skirt, if you will. And that matter is extremely rich in neutrons because a neutron star is mostly just a bunch of neutrons. It's like a gigantic nucleus. And the fact that you have so many neutrons floating around after this event means that it's much easier to produce extremely heavy elements, which, as you may know, need to have an excess of neutrons in order to form. And so that is something I'll come back to in just a moment, the idea that there's a lot of extra neutrons floating around after this merger. Now, we had coordinated with about 70 different groups around the world who had optical telescopes and X-ray and gamma ray satellites, radio telescopes, even a neutrino observatory in Antarctica. So when we would see something interesting, we would send them a signal saying, hey, we think we saw something in the sky at roughly that location. Maybe you should go take a look. Okay, so getting back to this idea of triangulation, if you looked at the signals from this pretty strong signal to noise ratio event from Hanford and Livingston, that gave you basically these two blue bananas. So two regions on the ring on the sky that were favored by the two observatories, Hanford and Livingston. Now, you might recall that we looked at the Virgo spectrogram and didn't see anything. And you might think, oh, well, Virgo's not helping. But that's not correct. The fact that Virgo didn't see anything is like the dog that did not bark in the night in the famous Sherlock Holmes story. It was significant that Virgo didn't see it. That meant that the place on this ring that was consistent with Virgo's not seeing it had to be close to what's known as the node in the antenna pattern of Virgo, meaning a place for which Virgo had very poor sensitivity. And so that told us that the source had to be pretty much right there. This is a figure taken from a paper that had many different measurements in it. We have our gravitational wave measurements, we have gamma ray measurements, we have X-rays, ultraviolet, lots of optical telescope measurements, infrared, and radio. The light was seen in all of these different wavelengths. And so one of the striking features of this event is that if you look at the spectrum, the amount of energy you saw as a function of the wavelength of the light seen electromagnetically, it evolved very rapidly from this peak at roughly 4,000 angstroms, roughly half a day after the merger, to something that peaked at much longer wavelengths in the infrared regime in about a week. And that was a characteristic that had been predicted as being a quality expected from what's known as a kilonova, which is this process by which all these neutrons come together to form very heavy elements. And in fact, we think that this is what led to the production of a lot of gold and silver and platinum and uranium. There's pretty good reason to think that most of the heavy elements like that in the universe, including what's here on my finger, a wedding band made of gold, that all of that, or at least a large fraction of it, came from the process of neutron stars merging together. This is a picture that appeared in the Business Insider magazine, showing you a artist's depiction of all of this gold and platinum and silver being produced. Business Insider found that interesting because they were probably thinking in these kinds of terms. But let me come back to that in a second. There were some estimates made, I would call them back of the envelope estimates, of how much gold was produced. One estimate was an amount of gold greater than the weight of the Earth, which is a lot. Someone else thought it was actually 10 times the mass of the Earth in both gold and platinum. And then someone else put a financial value on it. And then someone else thought it might be 200 Earth masses of gold and 500 Earth masses of platinum. So we don't really know what the right answer is. It depends a great deal on the theoretical modeling of the process, but a lot of it was produced in any case. But one thing to watch out for is that this all happened 130 million light years away. So if someone comes to you and is asking for money to form an interstellar expedition to go fetch and harvest all that precious metal, be careful. It's not going to happen in your lifetime. Okay, so this shows you a summary of all of the black hole mergers and one binary neutron star merger that we saw in our first two observing runs. And more recently, we ran the O3 run from April 2019 to March 27, 2020. We cut it short by about a month from what had been planned because of the pandemic. We had more sensitive detectors, both LIGO and Virgo were more sensitive than they had been, and we ran for almost a year. And so what we expected were dozens of black hole mergers, a few neutron star mergers, and perhaps a surprise or two. And what we actually saw were dozens of black hole mergers, at least one neutron star merger, in addition to the one we'd seen before, and we did see some surprises. This shows you a graph of the number of events seen of all types of mergers as reported promptly. I mentioned earlier that we would send out alerts to our partners. We started sending those out just publicly in the O3 run. And we sent out quite a number. We retracted a few of them after realizing that there was something in our data that misled us. But most of those were not retracted. Excuse me. And in addition, we saw some others that took a little bit longer to pick up in the data. We weren't able to detect them instantaneously. This shows you one of the surprising events. Again, these are spectrograms from Hanford, Livingston, and Virgo. You can see the signal in all three interferometers. What's unusual about this event is that there's a distinct asymmetry. The two black holes have distinctly different masses, which was something that we had not seen clearly beforehand. And then another event had that effect even more strongly. So 1908-14, August 14 of 2019, had 23 solar masses for one, but only 2.6 solar masses for the other. It was very well localized, in part because the signal lasted a long time in our interferometer. So here we have about a 10-second span of data for which we can see a signal. But there was no electromagnetic counterpart seen. And that was not a big surprise because we think it was pretty far away. And we don't even know for sure that we would see any neutrons spilling out of a black hole neutron star event that is this asymmetric. But there is a natural question. What is that secondary whose central value seems to be about 2.6 solar masses? This shows you a bit more information. This shows you the primary mass versus the secondary mass, showing you probability contours. Still, there remains the uncertainty of why the secondary mass has the value that it does. It's 2.6, and it could be a little bit lighter than that, but it could also be a little bit heavier than that. It's really too heavy to be a conventional neutron star. And yet it's very light for a black hole. It falls into what's known as the low mass gap. And that really challenges some of our ordinary models of stellar formation. And so we don't know what it is. We have an artist diagram here that shows you a black hole on the left and something over here that's either a small black hole or a very heavy neutron star. One possible explanation is that it is a black hole, but an unusually light black hole that was formed by the merger of two previous neutron stars. So something very similar to what we see what we saw in our very first neutron star merger, something that would have a mass in that ballpark quite naturally. We don't know. Here's another unusual event that was seen in the O3 run. It shows you little blobs in the spectrograms, and they don't look very chirpy. There's a hint of a chirpiness, but the reason they don't look very chirpy is that they're so short-lived. And the frequency at which they top out is just a little bit greater than 60 hertz. The fact that the final frequency is that low is telling us the two black holes came together very quickly and that they were massive. So when you have a short but strong signal that peaks at such a low frequency, that's telling you that you have a massive system. So how massive was it? Well, here's another one of these mass plots. And we see that one mass is up here in the ballpark of 85 solar masses. The other one is at about 66 solar masses. And those are surprising values themselves because of something known as a high mass gap. There's a process called pulsational pair instability that should really blow off most of the outside of a star that's in that mass range. Yet here we have two stars in that mass range between 65 and 135. So one possibility to explain that, assuming the ordinary stellar models are correct, is that each of these black holes itself was again a hierarchical merger, something that came together from the merger of lighter black holes. For example, the 66 could have been two 33 solar mass stars coming together, as an example. One other notable feature of this event is that the total mass, when they came together to form the final black hole, is about 150 solar masses. And that was the first detection in any realm, gravitational or electromagnetic, of a stellar level mass that was greater than 100 solar masses, as opposed to one of these very supermassive black holes that are, say, millions of solar masses at the core of a galaxy. So this shows you a graph of all of the black hole and binary neutron star mergers that we've seen to date. And we've also seen a couple of mergers of neutron stars with black holes. This shows you their order chronologically from the very first detection to the most recent detection in March of 2020. And you can see that the little yellow dots represent neutron stars, the blue dots represent black holes. The size of the dot represents the mass of it. And then there are a handful of ambiguous cases where we don't know if it's a black hole or a neutron star. We don't know for sure that when two neutron stars come together that they form a black hole, although that's by far the most likely explanation. So I see I'm running out of time, so I don't want to just keep rattling on. So why don't I zip to the end, and then I can take questions. So we've observed about 90 definitive mergers of black holes and neutron stars. Virgo has now started taking gravitational wave data with us and has seen signals. We've had 2 discoveries of binary neutron star mergers, and we had this stunningly successful electromagnetic follow-up campaign that led to the aftermath being seen in a whole bunch of different bands of the electromagnetic spectrum. And those observations strongly support a kilonova explanation for heavy element production in our universe. And we are now seeing some unusual binary black hole systems that challenge conventional models. We've seen asymmetric masses. We've seen objects in the lower mass gap, and at least 2 objects in the higher mass gap. Again, things that have not been predicted in advance. And of course, we've seen the formation of the first intermediate black hole with a mass greater than 100 solar masses. And there's more to come. We're going to take data again starting late next year. I think it's fair to say that we're well into the dawn of gravitational wave astronomy. The next 20 years should be eye-opening as we make more measurements, and the next century could be eye-popping. Thank you.
Thank you so much, sir, for such a mesmerizing and insightful lecture. And for sure, gravitational waves are a new lens to seeing the cosmos. The presentation was indeed an engaging one, and which definitely kept me glued to my screen. And I was really fascinated by how Ligo isn't the only game in town, which is when it comes to the hunting for gravitational waves. There are also several other detectors across the globe, including one in India, which we are trying to hunt for the minute signals from the wave across the globe. Thank you so much, sir, for enlightening us about them.
Well, yeah, it's my pleasure. I'd be happy to field questions.
Okay. So we'll now take up some questions which people have posted in the comment section. The very first question is from Priyanshu Mehto. The question is, do we regard the gravitational field as a tensor in GR?
Well, that's a somewhat technical question. We represent gravitational effects in a tensor way. The distortions I talked about, the gravitational waves, are themselves represented as a tensor. There's something called the Minkowski tensor, which would correspond to flat space, where there's no appreciable distortion due to masses. And then you can have a static perturbation of that, which would be appropriate for, say, the Earth's surface, where we do have a tiny little bit of warping of space due to the Earth's mass. And that can be described with a tensor. But then the gravitational wave comes along and it further perturbs that tensor away from the flat space. And it's really that little residual piece that we call the strain amplitude. But yeah, it's very appropriate to represent that in a tensor formalism.
Rishabh, you're mute.
Okay, thank you so much, sir. The next question is by Mohammed Sohail. He's asking, are gravitational wave events frequent?
Well, it depends on how you define frequent. We don't detect them frequently, but that's largely because of the limitations of our detector sensitivities. We're trying to improve upon that, and we can basically correct for the effects of our imperfect efficiencies by trying to estimate what the nominal rate is per unit volume per unit time in the universe. And so when we put together ensembles of events in what are called catalog papers, we give our best estimate of how many mergers there are per unit time, per unit volume in the universe. And so depending on whether you're looking at binary black holes or binary neutron stars, those can range between, well, basically tens to hundreds of mergers per year per cubic gigaparsec. Now, the universe is big, so if you keep looking further and further out in the universe, you'll see more and more of them as you sample more and more of the universe. I'm hoping, many of us are hoping, that by the mid-2030s, we will have new detectors on the surface of the Earth that are successors to the current detectors that would be so sensitive that they could see every single merger happening in the universe going back a certain amount of time. And what I mean by that is that if you can see far enough back in time, you can see to a time before ordinary stars were formed. And so you'll run out of sources. If you look far enough back in time, which is to say far enough out in space, you will see everything that encompasses the universe in which stars were formed. Um, and so that is something that is quite possible within the next 20 years that we'll be able to see that far back. Now, a really intriguing possibility is that we will keep seeing things that far back, that we will actually see mergers of black holes that happened before stars were formed. And that could happen if some of those black holes were not black holes formed by the collapse of gas in a galaxy somewhere, but were actually primordial black holes that were formed in the Big Bang itself. And so that's a very exciting possibility for the future, that we could detect primordial black holes directly and know for sure that they're primordial and not something that came out of stellar formation.
Thank you so much, sir.
This was really exciting. Okay, so the third question is from Ansh Gupta. Can gravitational waves cancel out each other like traditional waves?
Yeah, you could have an interference of gravitational waves in principle. Um, I wish we had that many gravitational waves to work with where we could actually look for that effect. So yeah, they're very analogous to light. They can constructively and destructively interfere. Probably the first evidence we're going to see of that effect will be eventually. We expect to see evidence of lensing of gravitational waves as the waves that come to us from some distant source pass in the vicinity of some other massive object. It might be simply a star, or more likely the core of a galaxy, some supermassive black hole. And when that happens, you can get some fairly dramatic effects where you actually get a perceptible distortion of the wave from interference. Um, so that's something we look forward to, and it's possible we'll even see it as soon as our next observing run. We looked for it in this past run, but didn't see any evidence of it. But it's something that is conceivable that we'll start to see an inkling of, is interference gravitational waves with themselves.
Thank you so much, sir. The next question is my personal question that I always wanted to ask.
Mhm.
So, before gravitational waves, the electromagnetic spectrum was the only way to explore the universe, and then we had the neutrino astrophysics to analyze the high energy environments in the universe.
Mhm.
But all these methods have a limitation that they transfer the information at or below the speed of light. So if two black holes that are 2 billion light years away from us, they merge today, we would only know about 2 billion years later using gravitational wave astronomy. So do you think there could be some method to know such events instantaneously?
I'm not aware of anything. I mean, there are these ideas of wormholes that allow you to sort of take shortcuts across the universe. Very speculative idea. Um, but we don't have any evidence of any wormholes out there. I mean, I guess people have occasionally claimed to see something odd in some electromagnetic spectrum that's been attributed to wormholes, but I don't know of anything that has held up to scrutiny. Um, but no, I'm not aware of anything like that. I mean, as you may know, quantum mechanics has a weird non-locality that's embodied in what's known as the Epr paradox. Um, but that's still not really a violation of causality. It's just something kind of very strange about quantum mechanics, that two events can happen uh, that are causally disconnected and are correlated with each other. Yet it's still not the same as sending a signal from one point to another faster than the speed of light. I'm not aware of any mechanism that could do that.
So we are always studying the past. We don't know what the universe looks like now. No one really knows.
Yeah, only the universe is immediately at hand, what you can see in front of you.
Correct. Okay. So our next question is from Joshua Demis. He says, how small can the gravitational wave detectors be?
Yeah, great question. If you make a gravitational wave detector too small, you run into the problem that it's hard to measure the dimensionless strain. I didn't have time to talk about it, but basically, the quadrupolar distortion I talked about is quantified in terms of a dimensionless strain, which is the fractional change in distance that happens when a gravitational wave passes by. And so, astrophysical objects that we look for have strain values at the level of 10 to the minus 21 or smaller, very, very tiny. And in order to measure something like that, you have to measure some displacement here on the surface of the Earth. I mentioned atometers earlier, and that's about the right distance scale to be thinking about. But in order to see something at 10 to the minus 21, if you have a displacement sensitivity at 10 to the minus 18 meters, then you need to divide that by something like thousands of meters, in other words, kilometers, in order to get down to that strain level. So if you make your gravitational wave detector smaller, then you need to have a much better, by orders of magnitude, a much better displacement sensitivity. And so that's very hard to do using the laser technology that LIGO and Virgo and Kagra are using. Another way to handle that, however, is to use a different wavelength altogether and to use atoms. And there are very serious proposals on the table, and people are doing interesting R&D on using, instead of laser interferometers, using atom interferometers, which have inherently much smaller wavelengths and in principle could sense small displacements more accurately. And so it's, that could well be our future. And if one can build atom interferometers that are much smaller than the scale here, it would be easier to isolate them from ground motion that plagues the ground-based observatories we have right now. And if you could suppress the disturbances due to ground motion, you could go to lower frequencies and detect sources that we cannot see with LIGO because the frequencies are outside of our band. We can't see anything currently below about 20 hertz. We're hoping eventually get down to about 10 hertz, but right now we're limited at 20 hertz. But with an atom interferometer in the future, one could imagine getting down to a hertz or smaller. And of course, there are also space-based ideas for getting completely away from ground motion, but those are a different kind of ball of wax to put a gravitational wave interferometer out in space. It will happen eventually, but it's, as you can imagine, quite a difficult enterprise.
Okay, that's something really astonishing. So the length of the 4 kilometer length will also reduce then because it will not be ground based.
Well, actually, the space-based interferometers are actually going to still be using lasers, and what they will actually try to do is lengthen the arms dramatically. One project called LISA, in its nominal design, has arm lengths that are millions of kilometers, and that allows them to probe down to frequencies in the ballpark of a millihertz or a 10 millihertz. And there are a lot of sources in our own galaxy that emit radiation, gravitational waves, at that frequency, just ordinary binary systems that are not anywhere near merging with each other, but are just steadily going around and around. And so that's a very exciting part of the future, again, for the 2030s.
Thank you so much, sir. The next question is by K. Gardner, and the question is, how were we able to convert the sound of gravitational waves generated from black holes to sound waves?
Well, the flickering of the light I talked about earlier is picked up by a photodetector, which is not so different from what you might have in your garage door for sensing when the door is open or closed, or when someone is passing by. It's basically converting the light signal into an electrical current. And so that electrical current is then digitized through something called a digital analog converter. So then it becomes a digital signal that can then be sent into our signal processing routines for detecting gravitational waves, which is a very sophisticated computer-based system. but it can also be sent directly into a, um, a converter that goes the other way. It goes from analog to digital, ADC. I said that wrong. Digital to analog, and then that analog signal can be run straight into a speaker. So an ordinary speaker you might have in your house, if you were to send an analog signal that has the same oscillations that are seen in the the gravitational wave data channel, would produce an audible sound. Um, so in what I've played for you, the sound effects I played for you, that's essentially what I've just done, is to take a digital signal and run it into whatever digital analog converter is in your own computer, and it has done that conversion.
Thank you very much, sir. Can we have the next question, Vishaka?
Yes. So the next question is from Anjali Shukla. How do we distinguish between gravitational waves originating from different sources like black hole merger, or the black hole neutron star merger?
It's basically determined by the frequency evolution of the signal. Um, to first order, what we see in the gravitational wave signal waveform is a frequency evolution that's governed by something called the chirp mass. And the chirp mass is a particular combination of the two masses, call them M1 and M2, of the primary and the secondary masses. And so the dominant part of the signal is just governed by that one parameter. But when you combine together the in spiral phase and the merger phase, and if you see a signal in the ring down phase, that too, um, then you can sort of disentangle things, and you're able to also see something in that waveform that depends on the two individual masses, M1 and M2. And so, um, just based on what those mass values are, we make a judgment as to whether we're looking at a black hole or a neutron star. We have good reason to think that neutron stars don't have masses greater than, or much greater than, about two solar masses. We have a pretty decent understanding of neutron star equations of state, and maybe 2.1 is allowed, maybe even 2.2, but it's hard to get much heavier than that with an ordinary neutron star. So if we see anything above 2.2, we're suspicious that maybe what we're looking at is a black hole. Now, in principle, when the two neutron stars come together, or a neutron star and a black hole come together, that there can actually be a disturbance of the waveform by the fact that the neutron star gets torn apart. As it comes together to merge with a black hole, that material in the neutron star starts just disintegrating. And that is, in some sense, robbing energy from the radiation process. And that should lead to a slight change in what we see in the gravitational wave. And we have looked for that, and we haven't seen any evidence of it. And so what we've been able to do so far is set limits on how deformable the neutron star can be. We're not really seeing any significant evidence of deformation. And so that just allows us to say, well, the neutron star is not this big fluffy thing that might be 20 kilometers in radius. We're pretty sure that's not the case. We think its radius is more like 12 kilometers, somewhere in that ballpark. And we're not sensitive with the data we've taken so far to anything smaller than about 14 or 15. Now, as our detectors get better, and particularly as they get better at higher frequencies, which is a range where it's relevant what's happening to the neutron star as a merger takes place, as we get better and better sensitivity at higher frequencies, we hope that we will start seeing the effects of that deformation. And when we do, then we'll be able to say more about the size of a neutron star, and also about how tightly bound it is. But right now we can't say very much at all. But perhaps in our next O4 run, which we hope will start at around December of 2022, about a year from now, perhaps by then we'll have enough sensitivity to see that effect.
So thank you very much, sir. So that would end the question and answer session. So, on behalf of the Secrets of the Universe and Gurukul Academy, I once again extend my hearty gratitude to Professor Keith Riles for accepting the invitation and sharing with us his valuable thoughts. Your thoughts have enlightened our minds and have shown us a new path. Here, I would also like to mention that these lectures are our endeavor to take global science to the students residing even in the remotest corner of the nation. Finally, I would like to thank all of you for joining us from different parts of the world. It is your love and support that keeps us going and inspires us to continue our work. Stay tuned on our channel for many such talks on the coming Saturdays. Thank you.
Thank you.
Thank you so much, sir. Thank you.